Okay, I am now sharing my screen. I hope everybody my screen. And can everyone hear me quite well?
Yes, sir.
Okay, thank you. Okay, let me just check the chat. Okay. Yes, so I think, yeah, okay. I think you can hear me well. Okay, you can see my screen also. Okay, thank you, everyone. Okay. For um, tonight, let's try to discuss about weight volume relationships in soil. Okay, in soils. Okay, so I think we know the basic definition of weight as well as volume. No? Okay. So in the case of soils, it's important for us to understand or to have some idea of the relationships between weight and volume. Excuse me for a while. Let me just. Okay. So apologies. So for a given volume of soil, okay, in a natural occurrence, so basically it consists of solid particles, okay, and also the void spaces between the particles. No? Okay, so for a soil, you have the solid particles, and then surrounding the solid particles are the void spaces. Okay, now the void space may be filled with air and or water. Okay, so it may be fully filled with air, or it may be fully filled with water, or it may be filled with both air and water. Hence, soil can be considered as a three-phase system. Okay, you have the solid phase, you have the air phase, then you have the water phase. Okay, so it's called a three-phase system. So if there is no water in the void space, then it is called a dry soil. Okay. But if the entire void space is filled with water, then it is referred to as a saturated soil. Okay. Now, however, if the void is partially filled with water, that means some parts of the void is filled with water, and then the other parts of the voids is filled with air, then according to Professor Das, who is the author of the book, The Principles of Geotechnical Engineering book, where I just simply got all these things where I presented here. You can just basically read the book. Um, According to Das, then he calls it a moist soil. Okay, but in my field of discipline, we can also call it an unsaturated soil. Okay, unsaturated soil. So that's why there is what we call also unsaturated soil mechanics. Okay, which I normally teach in the master's degree program. Okay? So for the moment, let's just call this as a moist soil. Okay. So in some literatures as well, you can also see a moist soil. So when you hear the words moist soil or partially saturated soil or unsaturated soil, that they basically mean the same thing. Okay. Yeah. It just depends on who is saying it. No? Okay. His choice of words. But basically, they are the same. That means that in a soil material, you have the solid part, okay, the solid particles, and then you have the voids surrounding the solid particles, wherein the voids, again, is filled with both air and water. Okay. So it is important in all geotechnical engineering works to establish relationships between weight and volume in a given soil mass. Okay. So here we have to define and develop non-dimensional volume relationships, such as the void ratio, porosity, and degree of saturation, which we'll define in a while. We also need to define and develop weight relationships, such as the moisture content and the unit weight, wherein the unit weight may either be dry, okay, dry unit weight, saturated unit weight, and a moist unit weight, no? Okay? Depending on the conditions of the soil below the ground, okay? In combination with the volume relationships. Okay, so let's try to define these terms further, no? Okay, in the next slides. Okay, so here we have two figures. Okay, so the left figure, okay, that's figure A. It gives you the soil element in a natural state. Okay, so please take note. You don't need to copy this because I just simply have taken this from the book. No, okay. If you have the book Principles of Geotechnical Engineering by Das, forward with the notes. So here on the left figure, we see here the soil element, the general soil element in a natural state. Okay, so basically here you see, say, uh, this dark shade with some spots. Okay, they are the solids. Okay, and then the dark spots with some lines. Okay, they can be the water. Okay, and then the white spaces there are the air. Okay, or yeah, they're the air. Okay, so that means the dark areas with lines um, is the water, as well as the white spaces here. If you can see my cursor, they comprise the voids. Okay, yeah. Then surrounded by the voids are these solids, no? The dark spots with the dots. Okay, so this is the soil element in a natural state. Okay, so if we consider this block, no? Okay, this block here. So this block has a total weight. Okay, so let's call it capital W, and then it has a total volume also. Okay, which is capital V. Okay? So on the right side of the figure, okay, so let's now try to delineate. Okay, so let's try to divide the solids, the water, and the air, okay, in this soil element. Okay, so if we try to divide them, then this is now the figure on the right. Okay, so the figure on the right, okay, so you now see here this. If you can see my cursor, I hope you can see my cursor. This part here is now your solid part. Okay, so we just lump all the solid materials here. We put it here. Okay, then we also lump all the water part. Okay, so we just combine all the water here. Okay, and then the remaining area is the air. Okay, so this is the one. So for the weight, okay, for the total weight, okay, so the total weight is now the weight of the solid, W sub S, okay, plus the weight of the water. Okay, now that's presuming that the weight of the air is negligible. Okay. Yeah. For the volume, okay. So the total volume, capital V, is equal to, or it's just the same as the volume of the voids, okay, V sub V, volume of voids plus the volume of solids, that's V sub S, okay? And then the volume of voids is equal to the volume of air plus the volume of water, okay? Okay, so I hope that's clear, okay? So just rephrasing it here. Okay, so we now have the total volume is equal to the volume of the soil solids. Okay, that's this one, V sub S, plus the volume of the voids. Okay, wherein the volume of the voids is equal to the volume of the water in the voids plus the volume of air in the voids. Okay, or the total volume is equal to the volume of the solids plus the volume of water plus the volume of the air. Okay? That's with respect to the volume. Okay, and then with respect the weight, wherein we consider the weight of the air to be negligible, then the total weight of the sample, okay, that's W, is equal to the weight of the soil solids plus the weight of the voids. So please try to remember this because later on, when we derive the other equations, we will just go back to these equations. No? So let's just call this equation 3.1, and then this one is equation 3.2. Just the same as the designation in the book. No? I just simply copy this from the book. Okay, okay, so that's 3.1 and 3.2. Okay, okay. So the volume relationships commonly used for the three phases in a soil element are the void ratio, okay, we call them the void ratio, the porosity, and the degree of saturation. Now, the void ratio, which is symbolized by small letter E, is defined as the ratio of the volume of voids to the volume of solids. Okay, so that's in equation form, the void ratio is equal to the volume of voids over the volume of solids. Okay, so if we go back to the figure, so the void ratio is equal to the volume. Okay, the volume of the voids, this one here, that's the volume of the voids over the volume of the solids. Okay, so that's what you call the void ratio. Okay, the small letter E. Then the porosity N is defined as the ratio of the volume of voids, but this time with respect to the total volume. Okay, so that's the porosity is equal to the volume of voids over the total volume of the soil sample. Okay, so if we go back to the figure, that is the porosity is now the volume of voids over the total volume. Okay, that means the higher the porosity, that means the higher is the volume of voids in comparison to the total volume. Okay, okay. Then the last one is the degree of saturation, which is symbolized by the capital letter S. Okay, now the degree of saturation is defined as the ratio of the volume of water to the volume of voids. Okay, so that's the degree of saturation. So if we go back to the figure, that is the volume of water divided by the volume of voids is what you call the degree of saturation, symbolized by the capital S. Okay. So let's just try to take note of these basic equations, because again, later on we will be using them in deriving the volume weight or the weight volume relationships. Okay? So I hope this is clear. If you have questions or clarifications, please call my attention immediately, or you can just chat in the box, no? In case you will forget your question. Please interrupt me anytime. You can ask me anytime, okay, while we are still here. Okay. Now, the relationships between void ratio and porosity can be derived, okay, using equations 3.1, 3 point, where's 3.3? 3.1, equation 3.3, and equation 3.4. Okay, so if you look at this one here, so again, the void ratio is equal to the volume of voids over the volume of solids, but the volume of solids is equal to the total volume minus the volume of voids. Okay. So because the total volume is equal to the volume of voids plus the volume of solids. Okay. So from here, if we divide everything by the total volume, okay, so this one will become 1. Okay, then you have here the volume of voids over the total volume. Okay, and then this one also. But we know that the total volume of voids, sorry, the volume of voids divided by the total volume is just equal to the porosity. Okay, so that means if we try to relate the void ratio and the porosity, then the void ratio is equal to the porosity N divided by 1 minus the porosity N. And then just doing some algebraic manipulations, then the porosity N is just equal to the void ratio over 1 plus the void ratio. Okay, just manipulate this equation. Okay. Okay. Now, with respect to the weight relationships, we also need to know the formulas for the moisture content as well as the unit weight. Okay. So the moisture content, small w, is also referred to as the water content. Okay. And it is defined as the ratio of the weight of water. Okay. That's the weight of water to the weight of solids in a given volume of soil. Okay. So that means if we go back to the figure, okay, the water content, okay, is the ratio between the weight of water over the weight of the solids. Okay, that's the water content, okay, or the moisture content. Okay, um, yeah, I think in this case, the water content can be treated as in this case, the water content is sometimes called the gravimetric water content, no? Because the weight is a function of gravity. Okay, yeah, it's it's mass times acceleration to gravity is weight. So that's why this can also be called a gravimetric water content, because there's also what we call as volumetric water content. Okay, that's in terms of volume. Okay. Um, Later on uh, in unsaturated soil mechanics, normally we try to um, understand, no? The behavior of the unsaturated soil mechanics in relation to gravimetric water content, volumetric water content, as well as the degree of saturation. Okay. Um, Now, um, so these parameters, okay, they are expressed in terms of percentage. No? Percentage. Now, we also have here the unit weight, which is symbolized by the Greek symbol gamma. Okay, it is defined as the weight of the soil per unit volume. Okay, it's just the same definition in your fluid mechanics. No? It's the weight, but in fluid mechanics, you have the weight of the liquid or the weight of the fluid over the unit volume. Okay, yeah. So the same here, only that here we are talking about soil mechanics. Okay, but the same concept with fluid mechanics, only that there you are talking about fluids. Okay. Okay, so the unit weight can also be expressed in terms of the weight of the soil solids, the moisture content, this one here, as well as the total volume. Okay, so if we go through this one here, so we know that the unit weight is equal to the total weight over the total volume, wherein the total weight is equal to the weight of solids plus the weight of water. If you go back to the diagram, no? If you try to imagine the diagram, okay, or if you have the book, you can also refer to the book in the figures in the book. Okay, so that's the weight of solids plus the weight of water over the total volume. Okay, and then if we factor out the weight of solids in the numerator, then you have the weight of solids is times 1 plus the weight of water divided by the weight of solids over the total volume. Okay? But we know that the weight of water divided by the weight of the solids is just equal to the moisture content or the water content, no? Based from this equation. Okay? So that means we can replace this one by the water content. So the weight is also equal to the weight of the soil solids multiplied by 1 plus the water content over total volume. Okay. So for soils engineers, they sometimes refer to the unit weight given in this equation, okay, as the moist unit weight, okay, moist unit weight, okay, or um, sometimes the unsaturated unit weight in our field, for example. Okay? So again, depends on whom you're talking to. Okay. So often in earthwork problems, okay, for example, when you are doing backfilling works, okay, for example, in construction, you need backfilling works, okay, there's some cut and fill works. Then one must know the weight per unit volume of soil, but excluding the water. Okay, so this weight is referred to as the dry unit weight, okay, or that is gamma
That in
sub
and of
D,
itself is
or dry unit weight. So in equation form, the dry unit weight is equal to just the weight of the soil solids divided by the total volume. That's excluding the water, okay? Because the total weight is equal to the weight of the solids plus the weight of the water, okay? So in dry unit weight, then it is just the weight of the soil solids divided by the total volume. Okay? So if we combine equations 3.10, no? If we combine equations 3.10 and 3.11. Okay. Then we can have this relationship here wherein the dry unit weight is equal to the unit weight, okay, or the moist unit weight, or it is sometimes also called the total unit weight, okay, over 1 plus the moisture content, okay, or the water content. Okay. So, for example, in laboratory works, you can probably determine the total unit weight. Okay. You can also determine the moisture content. You will be doing this in the lab. Okay. For your laboratory subject. So if you have these two informations, then you can compute for the dry unit weight. Okay. So, for example, in the geotechnical reports that we normally prepare, um, we normally provide the dry unit weight. Okay. Yeah. Okay. Now, in SI system or System International, the unit used for the unit weight is in kilonewtons. Okay, that's kilonewtons per cubic meter. Okay, that's kilonewtons per cubic meter, where um, where 1 Newton is equal to kilogram times meter per second square. No, okay, so that's a unit of force. Okay, so Newton is a unit of force, where force is equal to mass times the acceleration due to gravity, or that's kilograms times meter per second square. Okay. Now, because the Newton is a derived unit, so working with mass densities, okay, mass density symbolized by rho of the soil may sometimes be convenient. Okay? Now, the SI unit of mass density, okay, is in kilograms per cubic meter. That's this one here. Okay, wherein the density, okay, the mass density, okay, rho to the mass of the soil divided by the volume of the soil. Okay, so if it is weight, then if this unit weight, then this is the weight of the soil. Okay, weight over volume. Now, for uh, the dry density, okay, so for the dry density, okay, so that is symbolized by rho sub d. Okay, so this is density here. This is dry density in kilograms per cubic meter. Then that is equal to the mass of the soil solids in the sample divided by the total volume. Okay, where the total volume is in cubic meters. Okay, and m is also the total mass. Okay, so just the same formula for the unit weight and the dry unit weight, only that here we are using total mass and mass of the soil solids, but in terms of unit weights and dry unit weights, we use here the total weight and the, the weight of the soil solids. Okay. Okay. So again, the unit weight is in kilonewtons per cubic meter. Okay, and this can be obtained from densities. Okay, if you have the densities in kilogram per cubic meter. Okay, so if you have the density here, okay, that's rho in kilogram per cubic meter. You multiply that by the acceleration due to gravity. So this becomes kilogram per cubic multiplied by meters per second square. Okay, so kilograms meter per second square will become newtons. Okay, that will become newtons per cubic meter. And then if you divide that by 1,000, then that will become kilonewtons per cubic meter, which is the unit of the unit weight. Okay. The same for the dry unit weight. it is just equal to the dry density, okay, dry density times the acceleration due to gravity. Okay, so that's the dry density is kilogram per cubic meter multiplied by meters per second square. So kilogram meter per second square will become newtons, okay, which is a unit of force. Okay, and then you will have now newtons. Sorry, if you, I hope you can see my cursor. You now have newtons per cubic meter. Divide that by 1,000 will give you kilonewtons per cubic meter. Okay, so we are just trying to relate here the unit weights and the densities. Okay, where the acceleration due to gravity is equal to 9.81 meters per second square. So that means that the unit weight of water is equal, in the case of water, is equal to 9.81 kilonewtons per cubic meter, or that's 1,000 kilogram per cubic meter. Okay. Okay. So here we are going back to the phase diagram. Okay, the phase diagram. Okay, it's just the same. Wherein here, sorry, wherein here you have again the total weight. You have the total weight. Okay, but this time, let's presume that the volume of the soil, okay, the volume of the soil is equal to 1. Okay, here. Okay, the volume of soil is equal to 1. So if the volume of soil is equal to 1, then we know that the formula for the void ratio is equal to the volume of voids over the volume of solids. But if the volume of solids is assumed to be equal to 1, in this case, in this particular condition, then the volume of voids is just equal to the void ratio. Okay, and if that is the case, then the total volume is equal to the volume of voids plus the volume of solids, but the volume of solids is equal to 1, then the total volume is just equal to 1 plus the void ratio, assuming that the volume of solids is equal to 1. Okay. And then the volume of water, okay, is now equal to the water content, okay, water content times the specific um, gravity, no? Times the specific gravity, wherein we will define the specific gravity in a while. Okay. Then here for the weight of soil solids, then that can be equal to the specific gravity multiplied by the unit weight of water. Okay. And then for the weight of water, that can be equal to the water content multiplied by the specific gravity, okay, of um, the specific gravity of the soil solids multiplied by the unit weight of water. Okay. Yeah. Okay. Okay. So again, to obtain a relationship among unit weight or density and void ratio and moisture content. So again, we can consider the volume of the soil solids to be 1. Okay. And then if the volume of the soil solids is 1, then the volume of the voids is numerically equal to the void ratio E. Okay. And then with this, again, the weights of the soil solids and the water is now given by these two equations, okay? Wherein the weight of the soil solids is equal to the, the unit weight of water, okay, uh, times the specific gravity of the soil solids, okay? Um, Wherein the specific gravity of soil solids, okay, is equal to um, the weight, no? The weight of the soil solids over the volume of the soil solids, which is just basically equal to the unit weight of the soil solids, okay, over the unit weight of water. No? So the weight of the soil solids divided by the volume of the soil solids, that's equal to the unit weight of the soil solids. Okay. So if you divide the unit weight of the soil solids by the unit weight of water, that will give you the specific gravity of the soil solids. Okay. Yeah. So that gives you, okay, so if the volume of solids here is equal to 1, okay, then that this will become 1. So that means the weight of the soil solids will now be equal to the specific gravity of the soil solids, multiply that by the unit weight of water. Hence, we now have this equation here. Okay. And then the weight of water is now equal to the weight of the soil solids multiplied by the water content, because we know that the water content is equal to the weight of the water divided by the weight of the soil solids. Okay, by definition of water content or gravimetric water content. Okay, but from here we know that the weight of soil is equal to the specific gravity of the soil solids, G sub S, uh, multiplied by the unit weight of water. Hence, the weight of water is equal to the water content multiplied by the specific gravity of the soil solids multiplied by the unit weight of water. That's why in this diagram, you are having these equations here. Okay. And that's with the assumption that the volume of the soil solids is equal to 1. Okay. Okay. So, using the definitions now for the unit weight and the dry unit weights in equations 3.9 and 3.11, where's that one? So that's let's go back. That's 3.9 and 3.11. Okay, so go back here. Okay, so the unit weight now is defined as the total weight over the total volume, but the total weight is equal to the weight of soil solids plus the weight of water over the total volume. But we know that the weight of soil solids is equal to the specific gravity of the soil solids times the unit weight of water, which is this one here, okay, which is the same as this one here, okay, plus the weight of water, which is equal to the water content times the specific gravity of the soil solids times the unit weight of water, which is now the weight of the water. Okay, divide that by the total volume. But from this diagram, we know that the total volume is equal to 1 plus the void ratio. Okay? So that gives you this one here. So if we just factor out the specific gravity of the soil solids, sorry, of the soil solids and the unit weight of water, if we factor that out, then we now have here 1, or we factor out this 1, then what is left is 1 plus the water content, okay, over 1 plus the void ratio. Okay? So again, the unit weight can also be equal to 1 plus the quantity 1 plus the water content multiplied by the specific gravity of the soil solids times the unit weight of water over 1 plus the void ratio, where again the void ratio is equal to the volume of voids over the volume of solids. Okay. Okay. So if we try to recall again the definition of the volume of voids, where's that? Okay. So just to recall, the volume of voids is equal, the void ratio is just equal to the volume of voids over the volume of solids. And then the porosity N is the volume of voids over the total volume. And then the degree of saturation is the volume of water over the volume of voids. Okay. So if we go back, okay, then for the dry unit weight, the dry unit weight is equal to the weight of solids over the total volume. But we know that the weight of solids is equal to uh, the specific gravity times the unit weight of water, okay, over the total volume, which is 1 plus the void ratio. So that's this one here. Okay. So that means you can also express the unit weight and the dry unit weight in terms of these parameters. No? So it depends on what is given in the problem. Or in actual practice, it depends on what is being provided by the laboratory. Okay? So normally, what we do in practice is when we do geotechnical investigations, we go to the field, okay, we do some drilling works, okay, so we try to extract samples, okay, from the ground. In my experience, the deepest we have drilled so far, um, yeah, just this last 2 weeks, so we were drilling. I think that the deepest we have drilled so far is about 50 meters. Okay, that's 50 meters, somewhere in Sorsogon. And every 1 meter or every 1.5 meter, we extract samples, then we send it to the lab, to the laboratory. Okay, then we have them tested with these basic parameters, no? The ones we are just discussing now. Okay, so this is the normal routine in geotechnical practice. Okay, so that's why it is quite important to try to remember them. If you will go into this practice later on, because in actual practice, this will just be the same parameters that you will be hearing every day. Yeah, okay. Okay. So if you just manipulate this equation here, then you can have the formula for the void ratio to be equal to the specific gravity of the soil solids multiplied by the unit weight of water over the dry unit weight minus 1. Okay. Um, so because the weight of water for the soil element under consideration is given by this formula, okay, based from the phase diagram, then the volume occupied, okay, by water can be given by this formula as well, okay, wherein we know that the unit weight of water is equal to the total weight of water divided by the volume of water, okay, But if we do some algebraic manipulations, we can also write the volume of water is equal to the weight of water over the unit weight of water. Okay. Okay. But we know that the weight of water is equal to this one here. Okay. So that's basically equal to, yeah, this one, weight of water. Okay. Then divided by the unit weight of water. So that means the volume occupied by the water, if you cancel out these two, is just equal to the water content multiplied by the specific gravity of the soil solids. Okay. So that means in normal routine, no, in normal technical routine, we always get or we always derive the water content. Okay. You can you also be doing this in the laboratory course. Okay. So when you have the water content, then you know the specific gravity of the soil material. Depending on the soil material, normally it's around 2.65 to 2.7, something like that, depending on the type of soil. Okay. Um, then multiply that by the water content, then that gives you an idea of the volume occupied by the water. Okay. So considering now the definition of the degree of saturation, symbolized by capital S, wherein the degree of saturation is equal to the volume of water over the volume of voids. Okay. But based from the diagram, we know that the volume of water is equal to the water content times the specific gravity, sorry, here's my cursor, times the specific gravity of the soil solids, and then the volume of voids is equal to the void ratio. So the degree of saturation now is equal to the volume of water, where the volume of water is equal to, from here, equal to the water content times the specific gravity of the soil solids over the volume of voids, but the volume of voids can just be equal to the void ratio, assuming that the volume of solids is equal to 1. Okay. So if the volume of solids is treated to be unity or 1, then we now have, from this equation, we now have the relationship between the degree of saturation multiplied by the void ratio is equal to the gravimetric water content. Take note, that's gravimetric water content. It is not volumetric water content. So that's in terms of weight. Okay, the gravimetric water content multiplied by the specific gravity of the soil solids. Okay. Now, in practice, this formula here is a very powerful formula. No? When you talk of geotechnical engineering practice, no? Even in the masteral program, when I teach advanced soil mechanics, we still go back to this formula. Okay, this is a very, this will be the starting basis of the derivation of the formulas for unsaturated soil mechanics. Okay? So this is a very powerful formula. Okay. Now, if the soil sample is saturated, okay, that is, the void spaces are completely filled with water. Okay, there's a figure here. Okay, that's this one here. Okay, so that means the voids now there is already fully filled with water. Okay, then here you now have the soil solids. Okay, so yeah, so from here again, if the volume of solids is equal to 1, okay, so then here the volume of voids, since there's no more air, then the volume of voids is now equal to the volume of water which is just equal to the void ratio, considering that the volume of solids is equal to 1, since the void ratio is equal to the volume of water over the volume of voids. Okay? So then the total volume is the same. It's 1 plus the void ratio. At this time, for the weight, since it is now fully saturated, there's no more air, then the weight of water is just equal to the unit weight of water multiplied by the void ratio. Okay. And then for the weight of the soil solids, that is the unit weight of water multiplied by the specific gravity of the soil solids. Okay. So this formulas here is with the assumption that the volume of solids is equal to 1 and it is fully saturated. Okay, that means there's no more air in your soil phase system. Okay, it now becomes a two-phase system, just the soil solids and the water. Okay, okay. So to derive now the formula for the saturated unit weight, okay, that's gamma sat. Okay, that's this is saturated unit weight, gamma sat. So that's now equal to the total weight over the total volume. But the total weight is equal to the weight of the soil solids plus the weight of water over the total volume. But the weight of the soil solids is equal to the specific gravity of the soil solids times the unit weight of water. That's that's gamma. Okay? And then the weight of water is equal to this one, which is now this one here. So the weight of water, okay, weight of water is now equal to the unit weight of water times the void ratio over the total volume, where the total volume is equal to 1 plus the void ratio. So if we just factor out the unit weight of water, then we now have here the saturated unit weight is now equal to the quantities G sub S, or that's the specific gravity of the soil solids, plus the void ratio multiplied by the unit weight of water over 1 plus the void ratio. Okay? And then from this equation as well, okay, from this equation, if the sample is fully saturated, that means the degree of saturation is equal to 100%. Okay. So that's for a saturated, that's in the case of a saturated soil sample. The degree of saturation is 100%, but if it is a dry soil, okay, as in oven dried soil, okay, in your laboratory, you will be bringing soil samples, you lab, and then you will put them in the oven. So that becomes oven dried. So that means there's really no water. That's really dry soil. Then in that case, the degree of saturation is 0. Okay. But in the field, there's no such thing as dry soil. Okay. In the field. Okay? There's only The only time you don't have water is when you oven dry, no? The sample in the lab. Okay. So in the case of a fully saturated soil, okay, so the degree of saturation is equal to 1. So that means here, the S part here in this equation is equal to 1. So that gives you then just the void ratio is equal to the water content times the specific gravity of the soil solids in the case of a saturated soil sample. Okay. Okay. So comparing now the two phase diagrams, so you now have here the phase diagram or the formulas of the weight and the volumes, considering a three-phase soil element, okay, with air, water, and solid. Okay, considering that the volume of solids is equal to 1, but on the right figure, okay, you have here the same condition wherein the volume of solids is equal to 1, but this time you have a saturated soil element. I just copy pasted the figures so that you can compare side by side the differences in the formulas for the weight of the water, then for the weight of the soil, okay, as well as the volume of the volume of the water, okay, considering or assuming that the volume of solids is equal to 1 for both a three-phase system or a saturated soil system. Or in the masteral degree, we also call this the unsaturated soil element. Okay. 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 So far, we have derived the unit weight, okay, the dry unit weight, as well as the saturated unit weight. Okay. But we can also express all of this in terms of densities. No? So we also have here the density, or you can also call it the total density or the moist density. Okay. Then you also have the dry density as well as the saturated densities. Okay. And then if you look at their formulas, this is just basically the formulas we derived for the total unit weight or the moist unit weight, okay, for the dry unit weight as well as the saturated unit weight, but only that we try to replace them by the density of water instead of the unit weight of water. No? Okay. So again, these are just basically the same formulas for the unit weights, only that we replace the unit weights by um, or the unit weights of water by the densities of the water, wherein the density of the water is equal to 1,000 kilograms per cubic meter. Okay. Yeah, that if you prefer to use densities. Okay. Okay. Now, earlier we tried to have some relationships with respect to the void ratio. Okay. Now, this time, let's try to have some relationship between the unit weight, the porosity, and the moisture content, okay, which can be developed in a manner similar to what we have just discussed earlier. But if we are now trying to consider porosity instead of void ratio, then instead of having the volume of solids equal to 1, we can have the total volume to be equal to 1 this time. Okay. So just to recall, the porosity is defined as the volume of voids over the total volume. Okay. So which means that if we assume now that the total volume is equal to 1 this time, uh, then so if this is now 1, if the total volume is now 1, then the porosity will just be equal to the volume of voids. No? Okay. And then the volume of um, um, then the volume of solids will now be equal um, 1 minus n. Okay, because the total volume, sorry, the total volume is equal to the volume of voids plus the volume of solids. Okay, but if the total volume is equal to 1, then the volume of voids is just equal to n. So that becomes the total volume of 1 is now equal to the volume of voids plus n. Or now the volume of solids is now equal to 1 minus n. Okay. So okay, so if we now have the diagram for that, okay. So considering a three-phase element, if we now find that the total volume is equal to 1, okay, it's now equal to 1, then by definition of porosity, which is equal to the volume of voids over the total volume, then the porosity in this case is just equal to the volume of voids. Okay, then the volume of solid will now be equal to the total volume, which is 1, minus the volume of voids, which is now equal to n. Okay. So with that, then the weight of the soil will now be equal to the specific gravity of the soil solids. Multiply that by the unit weight of water, okay, times times the volume of solids. Okay, but the volume of solids is now equal to 1 minus n. Okay. And then for the volume of water, oh, sorry, the weight of water is now equal to the water content times the specific gravity of the soil solids times the unit weight of water multiplied by the volume of the soil, but the volume of the soil is equal to 1 minus n. Okay. And okay, so that's now this one here. Okay, so if we try to, again, to recall, the weight of the soil solids is equal to the specific gravity of the soil solids multiplied by the unit weight of water multiplied by the volume of the soil solids, but the volume of the soil solids is equal to 1 minus n. Okay? And then for the weight of water is now equal to the water content times the weight of the soil solids, because we know that the water content is equal to the weight of water divided by the weight of the soil solids. Okay. Okay. Um, so, but we know that the weight of the soil solids is equal to this one. So then we just replace this weight of soil solids by this term here. Okay, this one. Okay. Hence, you have these two equations here. Okay. Okay, so that is okay. So with that, we can now derive the dry unit weight. Okay. So for the dry unit weight, is just equal to the weight of the soil solids over the total volume. But we know that the weight of the soil solids is, where's that? Weight of the soil solids is equal to this one. Okay. So that's this one here over the total volume, but the total volume is assumed to be equal to 1 if you don't know. For example, in some problems, you don't know the total volume, then you can assume that the total volume is equal to 1. And so then you can use these formulas. Okay? So that means the dry unit weight is just equal to this formula here. Okay? That is the specific gravity of the soil solids times the unit weight of water multiplied by 1 minus the porosity. Now, for the moist unit weight, so we know that the moist unit weight or the total unit weight, okay, um, is equal to the total weight. So the weight of the soil solids plus the weight of water over the total volume. Okay. So if we now substitute the weight of soil and the weight of water, again, by these formulas here, these two formulas, we substitute it here. Then you factor out 1 minus n. So that will leave you the quantity 1 plus the water content multiplied by the specific gravity of the solids multiplied by the unit weight of water over 1, because the total volume is considered this time considered to be 1. Okay. Now, in the case of is saturated soil, okay, this one here, okay, this figure here. So this time we only have a two-phase element, okay, the same story. We only have the soil solids, okay. Then the voids is fully occupied by water. So again, if we presume that the total volume is equal to 1, so still you have here this time the volume of water is still equal to the porosity because the total volume is 1 as per the definition of porosity. But since this is now fully saturated, then the porosity is now equal also to the volume of voids, okay? Because there's no more water, which is just equal to the volume of water. So with that, then the weight of the water is just equal to the unit weight of water multiplied by the porosity. Earlier, when the volume of solids is equal to 1, then this one is basically the void ratio, okay, void ratio. But this time, since the total volume is equal to 1, then this one becomes the porosity, okay? Because porosity is related to the total volume, while the void ratio is related to the volume of solids. Okay. Then for the weight of the soil solids is still the same. This one here. Okay. Um, so in the case of the saturated unit weight now, so we now have the weight of the soil solids plus the weight of water. But again, we know that this is now the weight of the soil solids, just the same. But this time, for a saturated soil sample, the weight of water is now equal to the porosity times the unit weight of water over the total volume, which is equal to 1. Okay? So just factor out some terms here, or the unit weight. Then you now have 1 minus n times the specific gravity of solids plus the porosity. Okay. So that's for the saturated unit weight. Okay. Now, for the moisture content. Okay. Now, in the case of the moisture content of a saturated soil sample, where we know that the degree of saturation of a saturated soil sample is 100%, but for the saturated water content, uh, by definition, we know that the water content is equal to the weight of water over the weight of the soil solids. Okay. So if we just replace this by the formulas, okay, sorry, we just replace it with these two formulas, okay, substitute it here, then we can cancel out the unit weight of water. So what is left is just the porosity over 1 minus n, or 1 minus porosity times the specific gravity of the soil solids. Okay, that's for the saturated water content. Okay, so again, just to compare the two diagrams, I just copy pasted again the two diagrams for the three-phase soil element. Okay, this time with some air, and for the saturated soil element, this time with no air, fully saturated. But this time, the total volume is presumed to be 1. No? Okay, presumed to be 1. So then we can now compare their formulas. Okay, so with respect to the water content, okay, for the two soil elements, again, in the masteral program, we consider this as the unsaturated soil element. Okay, and then with respect to the volume of water as well. Okay, so these are just the differences in the formulas. Okay. Okay. Um, so here we now have a list, no? A list of the different formulas for the moist unit weight, the dry unit weight, and the saturated unit weight. Okay. So you can see here there's quite a number of formulas here. Okay, so we cannot derive all of these formulas, but you can derive them yourselves if you like. Uh, um, the book just gave us a list of the possible formulas that you can use depending on what is given or what is known, for example. Okay. Yeah. For example, if you want to compute the saturated unit weight, given the specific gravity and the saturated water content, then you can use this formula, for example. Okay. Yeah. Okay. So you can just try, if you want to practice deriving, then you can try to derive all these formulas. Uh, so if you don't want to derive, then you can just try to memorize all these formulas. Okay. So I suggest you start memorizing, because in the board exam, you might need to memorize all these formulas. Okay. 2 years from now, I guess. Okay. Um, I'm assuming you're third year now. Huh? Okay. Um, okay. But if you can forget during the board exam, then you can also derive them, no? If you know how to derive them. For as long as you know the basic formulas. So basically, we just derive some of the formulas here, not all of them. Okay. So here we are just given some typical values. Some typical values for the void ratio, the moisture content. Okay, that's the void ratio, the natural moisture content. Okay, in the case of a saturated state, okay, saturated sample, as well as the that's in percentage. Okay, um, the void ratio is unitless. The void ratio is unitless. The moisture content in percent, and then the dry unit weight in kilonewtons per cubic meter. These are just typical values that you can find in the literature considering these different types of soil material. I think in the next lessons, we will be discussing the different types of soil materials according to the unified soil classification system. So these are just some descriptions of the unified soil classification system. So basically you have here sands, silts, clays. Loess is basically a wind-blown silt. Okay. A glacial till. A till material is basically a combination of clay, silts, sands, coals, and boulders. Okay. They usually happen because when there's, for example, there's an in temperate countries, okay, then we call them a glacial till. Okay. In Canada, for example, if you want to do um, some research work in Canada, okay, if you want to proceed to a masteral and doctoral studies in Canada, one of the popular soil material there is Indian head till. Okay, Indian head till. Okay, so it's I think the author of our book that I use in the masteral program, which the book on unsaturated soil mechanics, written by Professor Fredland from the University of Saskatchewan in Canada. Um, his one of his research work is about the Indian head till. No? Indian head till. It's basically a glacial till material. No? Of course, we don't have that material here in the Philippines because we don't have snow. Okay. Okay. Then Lewis, okay, these are usually wind blown, no? Wind blown cells. We call them Lewis. Okay. Yeah, so these are just typical values, no? That you can find. In practice, again, in the geotechnical reports that I prepare, okay, we provide dry unit weights, no? And these are also the values that we normally provide around this range, okay, um, for different types of soil material, depending on what we can find from the geotechnical investigation. So we describe that, we give the descriptions per depth, no? Okay, per depth. Then we make we make what we call as an ideal visual profile. Okay. Okay. So let me see. Okay. 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 So now we also have the term relative density. But before we go to this one, let me just rest for 10 minutes. Okay. Let me just rest my voice. Okay. The time now here in my watch is 7 7:25, I think. Okay. Please be back by 7:35. Okay. Let's have a 10-minute break. Okay. You can have your some personal break as well. No, you can have some toilet break. Okay. While I rest my voice. Okay. There seems to be a change. Okay, go back one slide. Okay. Okay. So while having your break, okay, let me just leave the slide here for everyone to see. Okay. So please be back by 7:35. Okay. It's now 7:25 in my watch.